We continue our study of probability distributions by now learning about a special type of probability distribution, a family called binomial probability distributions. Here we'll not only introduce what constitutes a binomial probability distribution, but we'll also look at some methods for calculating those probabilities and also finding the mean and standard deviation for binomial distributions, and ending with a way for determining whether certain results are significant, either significantly low or significantly high. First, we'll start by saying that binomial probability distributions are probability distributions, so they must first satisfy the three requirements for all probability distributions that we saw in the previous section. The first of those three requirements is that we must have a random variable x that is numerical and represents outcomes that occur by chance. The second requirement is that the sum of all those probabilities must equal 1. And the third requirement is that each individual probability had to be a number between 0 and 1 inclusively. We have 4 additional requirements for a probability distribution to earn the label binomial. The first of these 4 additional requirements is that whatever procedure we're carrying out must have a fixed number of trials. Not only must it be countable, but it must be finite. A trial is a single observation. Second requirement, these trials must be independent, meaning that the outcome of any individual trial cannot affect the probabilities in the other trials. The third requirement is what actually earns the prefix bi for binomial. Each trial must have exactly 2 categories of outcomes. One referred to as a success, the other one as a failure. So think about each trial as having 2 possible outcomes, either a success or a failure. And finally, the fourth requirement is that the probability of a success must remain the same from one trial to the next. Let's introduce some notation here. We will use the letter S to signify a success, F for failure. The probability of a success is going to be denoted with a lowercase letter p. The probability of a failure is equal to 1 minus p because, of course, a success and a failure are complementary events. But we'll also introduce another notation here. 1 minus p we will label as q. So q is going to denote the probability of a failure. And finally, n is going to represent the fixed number of trials. X is our random variable, and it is going to count the number of successes among the n trials. So x can be any whole number between 0 and n inclusively. So for instance, let's say that we had 5 trials, and x is counting how many of those 5 trials ended in a success. Well, it is possible that none of the 5 trials ended in success. They were all failures. In that case, x would be 0 successes. It could be that among those 5 trials, we only had 1 success and 4 failures. So in this case, x would be 1 success exactly, and so on and so on. X has a maximum value in this example of 5, which would indicate that all 5 trials were resulted in successes. P is the probability of success in one of those n trials. Q is the probability of failure for any one of those n trials. And the label P of x is going to stand for the probability that we get exactly x successes among the n trials. We want to be very careful that when we talk about successes and failures, that we don't associate the 2 outcomes with a success being necessarily a positive thing and a failure being a negative thing. A success is whatever outcome we're interested in counting. So for example, if we're looking at patients at a hospital and we're looking at death rates, having a patient die may be considered a success if that is what we're counting. Obviously, that's not what we ever would desire. We also want to make sure that when we are defining what X and P and Q stand for, that we are very clear that X is the number of successes and should be partnered with P, the probability of a success, and then N minus X would be the number of failures, right? Everything that's not a success must be a failure. So N minus X is the number of failures, and that number would be associated with Q, the probability of a failure. Let's look at this example. Let's suppose that we know that if we were to randomly select an adult from a very large population, that the probability that that adult is cashless, meaning the person is not carrying cash on their person, that there's a 0.05 probability of that happening. Doesn't ever carry cash. And this is actually data coming from the US Bank survey that included over 2,000 adult smartphone owners in the US. If we take this information to be true, we want to find the probability that among 10 randomly selected adults, exactly 2 of them will be cashless. First, we have to determine if this constitutes a binomial distribution. So let's go through the 4 requirements. If we do determine that it is a binomial distribution, we'll want to define what the values of N, X, P, and Q would be. First requirement, do we have a fixed number of trials? Yes. Randomly selecting 10 adults would be considered 10 trials if we think of a trial as being a selection. So making 10 selections would give us 10 trials, which is a fixed number. So the first requirement is met. The second requirement, the 10 trials would have to be independent. And I think we can assume that this is true because we are making the selections with replacement per the previous slide. So whatever outcome happens with one selection has no bearing on the outcome of any future selections. Third requirement, do we have exactly 2 possible outcomes for each trial? I think we do. Each trial is a selection of a person, and that person either is cashless, which would be a success, or is not cashless, which would be a failure. So yes, we have 2 possible outcomes. And finally, the fourth requirement, for each randomly selected adult, we would have to have the exact same probability of success over all of the trials, and we can verify that there is a 0.05 probability that any of these 10 selections individually will have a success, meaning that that person will be cashless. So now that we have verified that we have a binomial distribution, let's look at the question that was posed. We wanted to find out if we were to randomly select 10 adults, the probability that exactly 2 of them would be cashless, meaning they never carry cash on them. Here, N is 10 because each selection is a trial. Number 2, we want to find the probability of exactly 2 successes, so X is equal to 2. Next, what does P stand for? P is the probability of success, which was given to us to be 0.05. Finally, Q is the probability of failure. If there is a 5% probability of having someone who is cashless, then there is a 95% probability that the person is not. Again, we find that number by subtracting the probability of success from 1. Again, a reminder that we want to be consistent. X is counting the number of successes, so that number should be paired with P, the probability of success. N minus X is the number of failures. That number should be associated with Q, the probability of a failure. We saw previously that there's a way for us to assume independence when there technically isn't, as long as the numbers are favorable. So when we're sampling without replacement, and the sample size is no more than 5% of the entire population size, we can treat the selections as being independent even though they technically would not be. I believe that because there are many, many more adult smartphone owners in the US than the 10 that we chose for our sample, that we easily can make the assumption of independence. Now let's look at how to calculate that probability of finding exactly 2 successes among n trials. And there are several ways for us to find the probabilities. First, we're going to introduce the binomial probability formula on this slide, but we also will be showing you how to use some technology for the more cumbersome calculations. The binomial probability formula looks a lot more intimidating than it actually is. Here we have the probability of getting exactly x successes among n trials is equal to n factorial divided by n minus x quantity factorial times x factorial times the probability of success p raised to the power x times the probability of a failure q raised to the power n minus x. I want to talk about a few things here. Some of you may have never seen the factorial notation before, and I want to explain what that is. N factorial indicates repeated multiplication by factors that are decreasing by 1 all the way down to a factor of 1. So for example, let's take 3 factorial. 3 factorial would be equal to 3 times 2, then times 1. So 3 factorial would be 6. 4 factorial, on the other hand, would be equal to 4 times 3 times 2 times 1, and that is equal to 24. So it's repeated multiplication starting with a factor of n and then multiplying by subsequent smaller factors, always subtracting 1, all the way down to a factor of 1. The other thing I want to point out here is that these two powers should make sense. If we have x successes, then we are multiplying the probability of success by itself a total of x times. And if all the other trials resulted in failures, meaning the remaining n minus x trials were failures, then it would make sense that we would have the probability of a failure repeated as a factor that many times. So let's look at how to find the probability that if we randomly select 10 adults, that exactly 2 of them are going to be cashless. Again, the probability that any individual is cashless is 0.05. The probability that the person is not cashless is 1 minus that probability, or 0.95. So using the probability formula given in the previous slides, we have the probability of getting exactly 2 successes as being equal to n factorial, or in this case 10 factorial, divided by 10 minus 2 quantity factorial, that's n minus x, times 2 factorial, which is x factorial, times the probability of success raised to the x power, where x is 2, times the probability of a failure times n minus x, not times, but raised to the n minus x power. After simplifying all these quantities, we find that the probability of having exactly 2 successes over 10 trials is 0.0746 when we round to 3 significant digits. That means that there is approximately a 7.5% chance that 2 of these 10 randomly selected individuals will be cashless. There is a way to simplify these factorial calculations so that you don't have to type them in manually as 10 times 9 times 8 times 7 all the way to 1. If you play around with your calculator a little bit, you'll find that exclamation point as one of the functions, and that stands for that factorial calculation. Now, let's look at another example. Based on a Gallup poll, 5% of U.S. adults are vegetarian. If we randomly select 5 adults, find the probability that, letter A, that exactly 2 of the 5 adults are vegetarian, and then as a separate question, find the probability that there are fewer than 3 vegetarians. Here it says that we're going to be using table A1, but we are not going to be using tables to calculate these probabilities. I'm instead going to show you how to use your calculator to do that. For the first question, we have n individuals, so n trials. we have the probability of success as being equal to 0.05, and we want to find the probability that x is exactly 2. When we enter this information into our calculator, we will find that the probability of having exactly 2 vegetarians among 5 people is approximately 0.021. Now I'm going to bring in the TI-8384 emulator to show you how to do that using appropriate steps. We're going to be looking for the binomial PDF command on our calculator that stands for binomial probability distribution function. It's going to take 3 input values, 3 arguments. We're going to put the value of n, comma, the value of p, comma, and the value of x, and it will give us the probability of having exactly x successes over n trials. The commands are as follows. We're going to hit the second key, and then we're going to go to the vars key, because if you see in small letters above vars, it says distribution. So here we're in the distribution menu, and we're going to scroll down until you find that binomial PDF command. In my calculator, it's letter A. It might be slightly different on yours. So we're going to go ahead and hit enter. It's going to ask us for the number of trials. In this case, n is 5. Next, it's going to ask us for the probability of a success. In our case, it's 0.05. Next, it's going to ask for the number of successes. We want 2 successes, so our x value is 2. And finally, we go down to paste, and it will type out what we have here on our screen. It's going to, here, let me scroll to the left so you can see it. This is the binomial PDF command, and in parentheses, we have n, comma, p, comma, x. Now when we hit enter, it will compute that probability for us, and that's where we obtain the 0.021 as our approximation. All right, let's take a look at part B of this question, which asked, what is the probability of getting fewer than 3 successes? So if we were to choose 5 people at random, what is the probability that fewer than 3 of them will be vegetarians? Well, fewer than 3 means 2 or less, 2 or less. So we could have exactly 2 vegetarians, or exactly 1, or exactly 0. I want us to rephrase fewer than 3 as being the same as having 2 or less, because the next function on our calculator is going to take the number of maximum successes that you would be interested in. So fewer than 3 successes means we would have a maximum number of successes of 2. Let's go back to our calculator and show you how to find that command. Because we're looking at a cumulative probability, we want to find the probability of exactly 2 vegetarians, or of exactly 1, or of exactly 0. Then we obviously could run the binomial PDF command 3 different times and add those 3 probabilities. Nothing would keep us from doing that. But a more straightforward way of answering that question is to enter it into the cumulative probability function for the binomial. So let's go back to second and vars, which is our distribution menu. And this time we're going to scroll down 1 more than we did previously until we find the binomial CDF command. So again, binomial PDF is our binomial probability distribution function. That's for exactly x successes. Here we have the binomial cumulative density function. That C means that we're looking at multiple values of x. We're going from x successes being 0 all the way up to a maximum number of successes. So in this case, we have the binomial CDF command over n trials, comma, with a probability of success equal to P, comma, with X or fewer successes. So let's go ahead and choose that command. We have 5 people being chosen at random. The probability of success is still 0.05. Here, the maximum X value would be 2. So we want at most 2 vegetarians. And when we go down to paste, it'll put that in the correct format. And when we hit enter, we see that we get a very high probability of 0.999 if we round to 3 decimal places. Now let's move on to how to compute the mean, the variance, and the standard deviation for binomial probability distributions. Of course, because these are probability distributions in general, we can go back to the techniques that we learned in section 5.1. But you see that by having the additional information that this is a binomial distribution, the formulas simplify very, very nicely. To find the mean of a binomial distribution, we simply have to multiply the number of trials by the probability of success. And therefore, let's go back. Let me see if sorry about that. So the mean for a binomial probability distribution is simply the number of trials multiplied by the probability of success. That could be a whole number. It also could be a decimal. So if it's a decimal, of course, we have to interpret that very carefully because we're looking at a whole number for X. The variance is also quite simple to calculate. It is simply N times P times Q. So number of trials times the probability of success times the probability of a failure. And of course, standard deviation is the square root of variance, so it would be the square root of that product. Now, let's look at how to determine whether results are significantly low, significantly high, or if they are between our 2 thresholds, then we consider them to be not significant or not surprising. I like to say to be expected. Same thresholds as before. Significantly low values are those that are further than 2 standard deviations from the mean on the left. Significantly high values are those that are further than 2 standard deviations from the mean to the right. Anything within 2 standard deviations would be considered not surprising and therefore not significant. So let's go back and take a look at a different example. We have an example that the book had previously. I did not cover it in the PowerPoint. I omitted it previously, but let's take a look at it now. If we have 460 overtime wins in the NFL football games, the number of trials would be 460. That would be N. The probability of success would be 0.5. The probability of a failure is 1 minus that number, which coincidentally is also 0.5. And this example was looking at a success as being winning the football game after having won the coin toss in the overtime. So the failure would be having won the game after losing the overtime coin toss. In part A, we're going to find the mean and the standard deviation for this example, and then we're going to, in part B, use the range rule of thumb to find a number of successes that would be significantly low or significantly high, and then we're going to use that result to answer part C. Is the result of 252 overtime wins in 460 games significantly high? So here we have the probability of success and the probability of failure as being equal to each other. N is 460, so the mean would be 460 times the probability of success, which is 230 games. That means that of 460 NFL wins, we expect that 230 of them would have also won the overtime coin toss. The standard deviation is the square root of N times P times Q. So in this case, that's about 10.7 games. Now, let's find out what values of x would be considered significantly low or significantly high. To answer that question, we're going to multiply the standard deviation, 10.7, by 2, and then we're going to subtract that number from the mean and add it to the mean to get our two thresholds. So here we find 230 minus 2 times the standard deviation would give us 208.6 games, and 230 plus 2 standard deviations would give us 251.4 games. Our interpretation, therefore, is that anything less than 208 games would be considered significantly low, and anything greater than 251 games would be considered significantly high. Here we have that same information repeated in text. As before, we also can look at probabilities to determine if a certain number of value for x is significant or not. Probabilities that are less than 0.05 cumulatively would constitute significant results. Finally, this last slide goes over some of what I said earlier in the binomial probability formula. It does seem a lot more intimidating than it actually is in practice. It is a little bit tedious to use, but I urge you to spend some time looking at this slide, looking at how the formula makes sense in terms of calculating these binomial probabilities.